image analysis. In this hands-on session, we'll explore the powerful intersection of deep learning and healthcare using Python, led by Dr. Ambli PS, Associate Professor at Reva University, Bangalore. You are in for an immersive experience into cutting-edge world of medical image analysis. To formally introduce Dr. Ambli, I would like to invite our teacher, Ms. Sarthana Behan.
Good morning, everyone. Welcome to the second day of our national seminar and workshop on artificial intelligence and machine learning. Today will be another fruitful day to enhance your knowledge in AI and ML. Today is dedicated for workshop with hands-on session and deep learning for medical image analysis using Python. For that, we have a distinguished resource person, Dr. Ambli PS. She is currently working as Associate Professor, School of Computer Science and Applications at Reva University, Bangalore, and she has over 20 years of teaching experience and more than 13 years of research experience. She is a passionate academician, researcher, and possesses good leadership abilities. She earned her PhD degree in computer science from Anna University, Chennai. She is a research supervisor at Reva University and currently guiding 6 PhD scholars. She is an expert in the core areas of data analytics, data mining, artificial intelligence, machine learning, and deep learning. She has into her credit to publish the Indian patents and over 23 papers published in international and national conferences and reputed journals. And also she is a reviewer of me. And she is an excellent trainer. And over 23 papers. Over 23 papers published in reputed international journals, conferences, and book chapters, and reviewer of many international journals. She is an excellent trainer and acted as resource persons to many faculty development programs and national level workshops. Also served as keynote speaker, session chair, and technical program committee member in many international conferences. She also serves as Board of Studies Coordinator of School of Computer Science and Application and also the Academic Auditor of Kerala Technological University. We are very fortunate to have Dr. Ambli PS here with us, sharing her knowledge and expertise in the field of deep learning. On behalf of Bharathamata College and Department of Computer Science and everyone present here, I extend a warm welcome to Dr. Ambli PS and I request her to take over this session. Thank you, ma'am.
ലൈറ്റ് പണിയാണ്.
ഓട്ടോ വലിയ സെൻസിൽ കഴിഞ്ഞോണ്ടിരിക്കുകയാണ്.
For giving me the opportunity, and thank you Alvin madam for the nice introduction. I know all of you are waiting for the session in deep learning for medical image analysis. So both this are just terms like deep learning and image analysis. I could find most of the students over here. All of you are from similar background, I feel, right? Any other people than students? How many of you are students? Please raise your hands.
അപ്പൂടെ ഭയങ്കര
Okay. This AI, ML and deep learning, all these concepts, nowadays all these things have applications in many areas, and mainly it has applications. It is helping our healthcare and agriculture sector very more. All these technologies, they're helping our healthcare and agriculture sectors more. And medical image analysis, a lot of developments have happened. And with the help of these technologies, we can do a lot of things. Let's have a look into that. First, my presentation will be including an introduction about this AI in healthcare. Then I have divided this session into two parts. Like in the morning session, I'll be taking the theory sessions along with hands-on, and afternoon you can dedicate fully for the hands-on sessions. I'll be sharing the programs, all the things with you. And in part one, I'll be dealing with the deep learning algorithms, very useful for the medical image analysis, and recent trends in medical image processing. And in the next session, part two, I'll be dealing with the medical images and analysis. These medical images, they are in different file formats, not in our ordinary JPEG file format or all. It will be containing a lot of information, and they may be in different file formats. And how to deal with these files in Python, that we will be dealing in the next session of our part 2, and how to do the image annotations in Python. All these things I will be discussing in the second session. Let me start with, all of us are aware that AI, everywhere AI is finding its applications, and we cannot even imagine of a world without our virtual assistants support from different places, which is enabled through the artificial intelligence. And the subsections of artificial intelligence like machine learning and deep learning. AI applications in So AI applications in healthcare. When we discuss about the AI applications in healthcare, mainly the applications are in medical imaging, diagnosis. So medical imaging in the sense when you go to some lab, take some X-rays, EEG signals or any other signals like the CT scan or everything, that will be the input for our system. And for diagnosing the disease, early detection of the diseases, this imaging will be helping. The medical imaging technologies, with the help of our deep learning algorithms, will be helping very much in the early diagnostics of diseases. All of us know that if a disease like the tumors or other diseases which will be having very serious effects, if they are found out in the early stages, the cure will be very easy. So this AI thing will be helping us, or our deep learning and machine learning algorithms will be helping us for the easy diagnosis and error-free results, like in the labs and all, when we are going with the analysis of these things, due to the human factors, maybe due to the input human errors, there may be errors in the output also. So these things and all can be avoided. And intelligent analysis, like the automated analysis, then predictions, radiology assistance, diagnosis in medical imaging, all these things can be done using the diagnostic part of the AI. And then it helps the physicians a lot. It helps the physicians a lot. All of us are reading the news every day, like the surgical robots. I think it's audible there. Last seats people, is it audible? Yes. Yes. Okay, no problem. So the surgical robots, they'll be doing, and remote surgeries and all, remotely, even no need of doctors going to a place and doing the things remotely, they can prescribe the medicines, even the e-Sanjeevani system and all. We have a different systems connected, even in the Indian scenario also we have a different systems. Like we have these things with support from people, and we can get the help of this medical practitioners without visiting them at the easiness of our home or at the easiness of other places. We can get the support from the medical practitioners. We can avoid long queues, all these things. Then alternative diagnosis, prescription, all these things are the supports given to the physicians by the AI systems. Then in patient care, even in the patient care, like the automated assisted diagnosis, real-time patient prioritization, health assistance, personal trainers, all these things are provided in the patient care sector of the healthcare. And then a lot of research and development is being happening in the AI in healthcare. Like we know when this COVID pandemic was there, it started for the first time. We were hearing these things for this COVID-19 was a new experience for us. And that time, even we were struggling like anything, and no medicines were there at the time. And this data analytics, all this helped a lot for this invention of this medicines, the drug discovery, like the vaccines for the COVID. It was enabled by the support of all the systems where huge data analytics were being done. And even when at the beginning and all the people, like we were collecting the data from the people, how they move, with whom all we were having contacts, all these things, how many days you had fever, what all symptoms you had. They collected all the data, and when they were able to do the analytics on the data, easy drug discovery or easy vaccine discovery was possible. And this AI support also was there. This helped the system a lot for easy discovery. Like this, lot of research is being happening in the healthcare sectors with the support of this AI, where automated things also are there, and the data in the analytic field also is supporting a lot. Then the vaccine development, all these are the results of the researches happening in the this healthcare field. So AI is supporting the healthcare a lot, and this healthcare sector is mainly into the processes which are happening there in the healthcare sector is mainly into the diagnostics, the physician supports, then the patient support, and then the easy detection of the diseases, vaccines, all these things. AI is supporting a lot. AI is the bigger, broader term, and this machine learning, deep learning will be coming as a subset of this AI. Then can I play a video? Just to take you to the what support this AI is giving in the medical sector. Just to show me 5 minutes, one video. Net is not connected. Internet is not connected. Just a quick video for the 5 minutes. Just take you to the innovations of AI.
We predicted that AI might take over human efforts for good, but this soon, it is really surprising. Artificial intelligence stands as a broad term encompassing a multitude of cutting-edge technologies, including machine learning, deep learning, natural language processing, and computer vision. And therefore, when we talk about AI in the context of healthcare, these technologies converge to create a powerful force that is reshaping the landscape of medical diagnosis. Stay glued, because we're going to explore what AI has to offer when it comes to making diagnoses and conducting treatment plans. The role of AI in medical diagnosis. One of the pivotal roles of AI in medical diagnosis lies in the realm of machine learning. AI's machine learning algorithms possess an unparalleled capacity to dissect vast data sets and uncover intricate patterns, oftentimes eluding even the most astute human experts. This ability has revolutionized the way we approach medical diagnosis, allowing AI to detect subtle trends or relations within patient data that can ultimately lead to more accurate and timely diagnoses. Deep learning algorithms, another subset of AI, have fundamentally transformed the world of medical imaging diagnosis. Think X-rays, CT scans, and MRIs. These complex medical images, once relying on human interpretation, are now subject to the scrutiny of AI. Deep learning empowers AI to examine these images with a level of precision and consistency that was once unimaginable. As a result, diagnoses are made faster, and potentially life-threatening conditions can be identified at earlier stages. When it comes to electronic health records, natural language processing algorithms play a pivotal role in harnessing the power of AI. These algorithms are skilled linguists, capable of extracting and comprehending vast amounts of medical data embedded in the text. They navigate the complexities of medical jargon, extracting valuable information from patient records, research papers, and clinical notes. This, in turn, for visual medical data, be it from endoscopy videos or dermatological images, by equipping AI with the ability to see and comprehend visual data. Computer vision has brought about a revolution in medical diagnosis. Conditions are identified swiftly, and nuanced and visual data that might escape human eyes are now within the realm of AI's expertise. How AI is transforming diagnosis. Gone are the days of relying solely on human interpretation of X-rays, MRIs, and CT scans. Today, AI-based image analysis is aiding clinical teams in detecting conditions, injuries, and abnormalities with unprecedented precision. Thanks to deep learning capabilities, AI can spot subtle nuances in these scans that even the most skilled clinicians might miss. This translates to quicker, more accurate diagnosis, saving both time and lives. In fact, AI hospitals are already becoming a reality, redefining traditional healthcare models. Brace yourselves, because AI is here to stay and dominate the future of healthcare. And now, let's talk about automatic positioning and centering of CT imaging. This process relies on AI algorithms to ensure that patients are positioned flawlessly within the CT machine. Why does this matter? Because proper positioning and centering guarantee that the images obtained are of the highest quality, providing the most accurate information for diagnosis. AI takes the reins here, using image analysis algorithms to determine the patient's anatomy's precise location. It then automatically adjusts the position of the CT machine's table and gantry to align with the desired image area. By considering previous scans and patient data, AI can even account for any movements or changes in the patient's anatomy. The result,
So here it
a
is
significant
exactly the
reduction in the
precision
time and
dedication.
manual effort required for positioning and centering, making the imaging process not only more efficient, but also more effective. This not only enhances the image accuracy, but also reduces the total radiation exposure to the patient. Now that's AI in action. Predictive analysis. AI is not just a buzzword, it's a game changer in healthcare. One of its superpowers is predictive analysis, which gives medical professionals a remarkable edge. This technology dives deep into patient data, sifting through known and unknown factors. With wisdom, using machine learning to decipher electronic medical records swiftly. It spots trends, suggests treatments, and makes sense of the data in a blink of an eye. AI through NLP becomes a partner in making healthcare decisions faster and smarter. It's not just about saving time and money, it's about saving lives. But wait, there's more. NLP's applications in healthcare are as diverse as they are game-changing. Let's explore three of them. Optical character rating. Decision support systems. These systems are tailor-made to assist healthcare professionals in making clinical decisions. They provide real-time patient-specific information that enhances decision-making and ultimately elevates the quality of care and patient outcomes. AI's impact on CDSS. In numerous studies, AI-powered CDSS has demonstrated its superiority over traditional decision-making methods in terms of accuracy, timing, and cost-effectiveness. For instance, research from the NCBI found that an AI-powered CDSS reduced time taken to diagnose a specific condition from an average of 6 minutes to a mere 36 seconds. Moreover, it's been proven that AI-powered CDSS can lower the cost of care for certain conditions when compared to traditional methods. Furthermore, these advanced CDSS reduce the risk of medical errors, a crucial consideration. Learn can be tailored to fit seamlessly into any healthcare system globally, eradicating the need for physicians to sift through volumes of medical journals or navigate complex databases. These advanced diagnostic processes aren't just the future, they are the present. As more healthcare professionals recognize the boundless potential of AI, it's only a matter of time before streamlined diagnostic processes become standard practice.
So, hope you had gone through this and noticed some terms like, again, AI, along with AI, we have the terms like machine learning, deep learning, precision medication, diagnosis, then it is taking less time, more accurate results, all these things you heard from this. And let me resume with my session. Now, let me just take you to the market view of this one. The 2018 to 25 data presented, the market share of 36% is being taken by the healthcare industry compared to the other people, like the manufacturing, financial services, and AI is playing a major role in this. Again, in the healthcare market, when we look into the healthcare market data, this is taken from the Global Telehealth Market 18 to 22 survey report. The market ratio, again, healthcare technologies are holding the major share, and AI and other assisted technologies are supporting the market like anything. Now, from where all this data is coming from? As we know, this input we are giving either as the medical images or any other data, from where all this data is coming. So this data may be coming from, all of us are aware, like maybe from the wearable devices, then other medical devices, then our scan machines, CT scan machines, smartphones, search engine data. All this data is contributing to the healthcare. All this data is contributing as the input for this, our machine learning or deep learning algorithms for the analysis. Then, see, let me just present a brief of the spectrum of algorithms there. We start from the early stages where only AI was there, like in the early 1980s and 1990s. Also AI was there, like the expert systems. We were that time all these people are new generation people. You may not be, you must not have studied or you must not have born to that age. Like you are all of you may be born after this 1980s or 90s, but all of you are hearing the term starting maybe from the machine learning. But I think before machine learning, AI also will be there in your syllabus, is it? AI also you are learning, right? The knowledge representations, all the schemes, all the things you are learning in this AI, right? Learning starts from AI. And then next time we had the expert systems, which were human programmed systems, where the knowledge is imparted to the systems, like the systems, expert systems like MySyn, and all were there in the medical, supporting the medical assistance systems were there. And then the growth started from this to the traditional machine learning. And the traditional machine learning started not in 2000s, early it started, the progress started in 2000s. And this machine learning algorithms are the mathematical algorithms proven to make the best results, best predictions, and I'm not going in deep to the machine learning algorithms and all. When you start with a machine learning course, you will be telling that there are different types of algorithms like supervised, unsupervised, reinforcement learning and all these things. I'm not going to the machine learning algorithms, so that if I go to the machine learning algorithms, I won't be able to complete even a small portion of my this whatever I expect to share. And then ours will be focus will be specifically on medical image analysis. So first I'll start with the typical algorithms and then I'll go to the medical image analysis. And then started the growth of machine learning algorithms, and neural network concepts was there in the machine learning. We had the traditional perceptron, multi-layer perceptron models and all. Then the deep learning, when it started evolving, we were more deep into the algorithms. Like we were focusing more on the neural network. As all of us know, deep learning is all about the neural networks. It's all about the neural networks. And so this will be having the progress. It started like with the machine learning algorithms. This deep learning algorithms also have the same characteristics, but for solving the complex problems like with the unstructured data or with the images and all, these traditional machine learning algorithms were not giving accurate results. They failed in some way, and this enhancement was supported by the deep learning algorithms, where we have the layers, more layers. We were following the neural network model where the back propagation works, weight balancing, everything is working. And then we were able to get more accurate results using this machine learning, the deep learning algorithms. And this is like the feature selected, how the feature is extracted, and how the classifications or predictions can be done. All this will be, when this is done using this type of algorithms, we can expect more accurate results in the case of the images or in the case of the unstructured data. So if I go to the imaging chain like we had in the video also you heard that we will be giving as input like our images, maybe the MRI scan or CT scan or the EEG or any PET or any images will be giving as the input, and there will be some process which is known as filtering. First I'll be going to the CNN first, then I'll show you more about the filtering process which is happening, which is a feature extraction process. And whatever we are giving the input image, from there the filtering process will be there and the processing is being done. Then analysis, and in this there are different steps like the segmentation will be there, masking will be there, and detailed segmentation. Or then in CNN we know there are many layers which we are going to deal with. And in this, finally, we will be getting the output, whatever classification we want. Like if we are giving an input image to 10 doctors and asking them to, if we are giving the scan report to 10 doctors and asking them what will be this disease or what exactly the prediction on this disease. Then like this people tell what exactly is the disease, we will get the output, what exactly will be the disease, or is the disease detected, like that we will get. And if with the help of these algorithms, we can advantages, we can early predict the things. If it is detected early, cure will be little bit easy, or it will be curable. We know in the case of the cancer and all the things, if it's identified in the last stage, cure may not be possible. And if it's identified in the beginning stages, it is curable. And like that, this early detection of the diseases is possible with this algorithms. This helps a lot. That's why it's evolving in the healthcare industry. Okay, now let me seriously move on to the paradigm of artificial intelligence, machine learning and deep learning. So all these terms are interrelated. Everywhere we are hearing all these terms. What's the relation between these terms? Artificial intelligence, if we are comparing these three terms with a human being, artificial intelligence is nothing but it emulates the human intelligence. The artificially, how the intelligence is imparted, that is artificial intelligence. And the machine learning is the human learning process, how a human being, or the best example will be a child, right? So when a baby is born, the baby don't know anything, and how it starts learning, and from this we are taking the examples and we are training the machines with the algorithms, and the machines, it is learning and it's giving the outputs. So machine learning is the human learning. It is a typical comparison with the human learning where we have a lot of algorithms and all involved for enhancing the learning process. And then deep learning is again the subset of machine learning. So this deep learning is not a separate entity. It is a subset of machine learning, which is a subset of the artificial intelligence. And all these terms are connected together. And this machine learning, deep learning, as I said, it is about the neural network. It's entirely about the neural network. And when it's compared with a human being, it emulates the networks of neurons in the human brain. How the neurons in the human brain works. I'll go to that. In the next slides. And next, I'll just give a comparison between machine. I told you, deep learning is a subset of machine learning, and how it is differing, or how what exactly is happening in the deep learning network and what exactly is happening in the machine learning network. So in the machine learning, when an input image is given, the feature extraction will be done. Classification is don't think that it's classification alone, but I have taken a typical example where the classification is done. And if a car is given as input and classified whether it is car or not, that is the classification process happening there. And these are two separate steps in the machine learning algorithm. It's a feature-driven learning. Like to do a task, knowledge is acquired from the input data, the features will be extracted, then the classification is done, and then it's giving the output. And in deep learning what happens, this feature extraction, classification, everything happens, and we have a set of hidden layers there. We have a set of hidden layers there where a lot of calculations are being done, weights are being calculated, and then maybe because based on there are different terms like bias, variance, all these things, weights are calculated, and if any based on the loss function and all based on the errors, again back propagation is being done, weights are balanced, and finally after a lot of training, finally the system is learning, and we are going to get the output. So the feature extraction and classification that's happening both there together. So here I have just taken one example, and you can just distinguish between what's happening there in the machine learning and deep learning. There in the machine learning we have two different steps for the feature extraction and classification, and here everything is happening there in the hidden layers. And here the problem, here one more enhancement is it's automatically discovering representations needed to understand features from the raw data. It's able to recognize features from the raw data, and even with the unstructured data, it's able to give some proper output. Now we know there are many developments like the generative things and all. This GAN and all is there, which will be able to produce different output. Even if we are giving like some input, we are giving it to learn, and it is able to produce some output. Like if we are using a lot of AI techniques for our, if your young face is given, you'll be able to produce your aged face, how your features will look like in the at your age of 70 or 80, like that aged face is able to produce. Like it is able to generate output, generate different outputs based on the learning process. So different enhancements are there in the deep learning. Okay. Now let me take some of the important deep learning frameworks where you can do your applications, where you can easily implement your work, some of the popular deep learning frameworks. So everyone, when you start doing some machine learning or deep learning projects or something, you will be hearing about some of these terms like Keras, TensorFlow, all these things, right? So here, there are different vendors. You can see there are different vendors and there are different products. And Google is a pioneer in this area, in the Python programming area. And this Google's TensorFlow is very popular framework for the deep learning. And mostly people are using this because it's very easy to use also. And this TensorFlow is a more popular framework for this deep learning. And it's an open source, most popular deep learning framework, and this is coded using Python. So as we all know, how many of you know the other languages, C++, Java and all? How many of you know other than Python? C++, Java and all, how many of you know? So then you can easily distinguish, right? It's very difficult to write simple programs also. It requires a lot of coding when you are writing in C++ or Python, and it's very difficult to remember all these things also. And the same code, same programs, when you are writing in Python, it becomes very simple. And that's why all the people are moving to this Python side. Okay, then Keras. Keras is a framework, but Keras is an API which can go with the TensorFlow. We'll be using the Keras APIs in TensorFlow environment. Mostly when you are doing the projects and all, you will be using the Keras APIs there. It's a Python interface also. And then Piano is there, the efficient manipulation and evaluation of mathematical expressions. For mathematical expressions, we'll be using the Piano. And then another two popular frameworks are Caffe and Caffe2. Caffe2 is the recent version. Caffe is the popular. Caffe was by the University of Berkeley. It was introduced by the University of Berkeley and it was written in C++. See, early when in 2000, before the popularity of this Python and all, the back propagation and all, neural networks and all, we used to write in C++, coding we used to write in C++. And it takes a lot of coding for all this, and it's very difficult task to code in C++, the back propagation networks and all. But in Python, when it is Python, it is very easy to write the code all. Then this CAFE is a friendly framework for computer vision. As we all know, these technologies are correlated, and the computer vision, the image analysis, computer vision technologies is very popular or friendly framework for this, and CAFE 2 is the enhancement of this by Facebook, and this is CAFE 2 like the image enhancements in computer vision techniques, then denoising of the images, then masking of the images, all this easily, colorization of the, if you get a black and white image, if you want to color the image, and all this easily can be done using this CAFE 2 framework. And again, this also you must have heard, PyTorch, Torch and all. These are also popular frameworks. And then by Microsoft, we have CNTK, Microsoft Cognitive Toolkit. And this is also an open source deep learning toolkit for building, training, evaluating neural networks. And then by the Amazon, this one, we have MXNet Gluon. Now all these technologies are tied up with cloud systems also. Whenever we are doing some processing, we will be storing, saving our data in the cloud. So all these are integrated only. So everything is integrated. And this MXNet and all is scalable and flexible with the advantage, the main advantage of this MXNet is it is flexible with multiple languages. So all the other frameworks we have seen open source, it is Python only. Mainly it is compatible with the Python, and coding will be done in Python only. But this one is compatible with C++, Python, Julia, MATLAB, JavaScript, Go, R, RSS, statistical analysis tool. So it will go along with all these things, but mostly all of us are aware whenever we are doing some projects or something, whenever we are developing our algorithms, we will be commonly using the PyTorch or TensorFlow, Keras, that we are going with all these things. Then, just let me quickly take you through the application of deep learning framework to medical image of human organs, like different analysis. I told that these are all techniques which I am going to tell. These are all the terminologies which I will be telling during the course of this session. Classification, then detection of the diseases, then diagnosis of the diseases, identification, image acquisition, monitoring, reprocessing, segmentation. How it is useful, I will tell you later. And then in the vast area of wherever it can be applied, like the neural head and neck, neural diseases, the many diseases are there related to the nerve system, neurological diseases, cardiac diseases, then skeletal diseases, abdominal, breast cancer, detection, prediction, early detection, all ophthalmology, so thyroid related things. So you can see all these algorithms which are given here, starting with like CNN, you can see the colorization there. It's having a lot of applications, and UNet is segmentation, mainly it's a deep learning segmentation algorithm, and then BGG. After that, the CNN and all, we had AlexNet, BGG, 16, 19, all these things, then ResNet applications, deep neural networks, then there are different algorithms. And again, one more thing which is of interest is this GAN, that is generative adversarial networks, which is almost supporting to the generative AI kind of things. Now we are all the time hearing the generative AI. It's able to give new outputs, whatever it is, whatever we are giving the input, it will learn. The encoders, decoders are all there, and it will be learning, and it will be able to produce different outputs. Whatever queries we are giving, it's able to produce different outputs. And like I gave you the example, like your face, the different postures, different the human face, like if you are giving your image at this age, what will be the expected feature at the age of 70 or 80? Your age aged pictures, or it's able to generate all this. That's a generate, the term you noted down. Generative AI, and the generative adversarial network. So that is a popular development in this area, CAM and all. And YOLO also you must have heard. YOLO is a computer vision algorithm, popular computer vision algorithm, YOLO. And this cafe, there are different algorithms, many algorithms are there that all the algorithms you cannot learn also, and even you have to have the basics of some one or two algorithms so that you can develop. That's the thing. You should have the basics of one algorithm at least, then you can develop on that. That's how it is being developed. See, if you read, you will be able to find out. First, some algorithms were there, the perceptron, MLPs and all, then the CNNs came, and then we can see from there lot of developments, research developments, all these are AlexNet, all these are different papers. The researchers found all this in different papers, and once they implemented it and once it came out, once it was giving good results, then it was stable there and other people started using it. So once you know one algorithm, you'll be able to develop the other things. Now, let me go a little more deep. So why is that? Everywhere we are hearing deep learning. Everywhere we are hearing machine learning. Earlier, some few years back, it was machine learning. Now everywhere we are hearing deep learning. Why deep learning has become so popular? Maybe some 4 factors if I tell. Maybe because of the data growth. Like earlier, for us, GBs were very big data. And then now the industry people are not even using the big data because every data is big data, it seems. That's why the industry also, they are not using the term big data because every data has become big data only. In exabytes, petabytes, every data has become very big. And this data growth, so when dealing with the bigger amount of data, large volumes of data, our traditional algorithms failed. And there we needed more training for the systems and more with the neural network kind of things, and we used to get the good output results. And then the evolution of this Python and the open source ecosystem. Earlier in some North American universities and all, they were using this Python programming. And here we were not using, in all the other places we were not using Python programming and all. It was a strange name for us. But later when this machine learning and deep learning technology started evolving, everyone found it very easy for doing our programming with this Python. So we started. Maybe this also paved way to the deep learning. And then the hardware advancement, we know earlier we were happy with our CPUs, processing capacities of our CPUs. Our programs were using the capacities of the CPUs and we were very happy with that. But later when we started doing this program, like when we are doing one image analysis, if we have a multi-class problem, like 3 types or 5 types of inputs are given, in one type itself we will be training some 500 or 1000 images. And then our CPU is not sufficient for doing the work. If you start training with this one, it will take days for completing the work. And in the multi-class problems, where we have, suppose we have 10 classes and in one class we have 1000 images, then in 10 classes if we are training, then we need more capacity for the CPU. So there this GPU started helping, and this GPUs enhance the graphical performance of the computer, and NVIDIA is the main contributor in this field. And in medium to large models, then video processing, everywhere this GPU started supporting. So in our labs also I told you, why? Because no need to store all these things in your systems. We can just go with the cloud things. Like you can save the thing, you can have the things in the images or all these things in the Google Drive, and then I'll go with the Colab for showing all these things instead of installing Jupyter or any other thing in your system. You can just go with the Colab. So the next one is the cloud and AI boom. So all these things paved way to this deep learning concepts. Okay, now I said that deep learning is everything about neural networks. And neural networks, the typical example, it is starting with our brain. Okay, so brain is the typical example of a biological neural network. It is a typical example for the it's a complex biological neural network, and maybe you may be remembering before some 4 or 5 slides, I compared these technologies with humans. So there we had found this neural networks. It had the idea from this our neural networking, biological neural network system. And in the brain, we know neuron, not even in the brain, in the other parts of the body also, neurons or the nerve cells. It is the action stimulator in the body. So whenever we are seeing, and we know the brain is coordinating all these things, and there are different, like some 4 lobes in the brain which is controlling all these things. We have the frontal lobe where the eyesight, all these things are there, and then movement, sensation, then the parietal lobe where the sensations, all these things are there. Like when we are first time when we are looking at something, we will be seeing that things, we will be identifying that object. For that, some neurons will be getting triggered, and we are able to identify an object. And then for the actions, like when we are going to touch the fire, or when people are playing, when one ball is nearing us, if a baby wants to catch a ball, so how 2 things need to be stimulated, right? So first it has to see the ball, and then next it has to move its hands for catching the ball. So these 2 things has to be coordinated. And this is done through our nervous system will be coordinating these things, and the coordination that is being, the nervous system's activities, it is being coordinated there in the brain. And the main part where it is being done is through these lobes, and there the cerebellum will be coordinating all these things. And let me move little more deep into the neuron structure. See, the neurons will be, so the lobes are there in the part of the body, in the brain. Different lobes are there, 4 lobes are there. And neurons, over 86 billion neurons are there in the adult brain. And this neurons are the basic unit of the brain and nervous system, transmitting information to and from the different parts. When one impulse is there, it is electrically excitable, and the impulse will be triggered. First, the impulse will be triggered, and its way is through the axons. So here you can just watch the impulse there. First, dendrites will be taking the impulse in, and primarily the electrical impulse is received in the dendrites, and then it is processed in the cell body, which is known as soma. So you can see the cell body there. I have marked the nucleus is there, and around that you can see the cell body where the thing is being processed. So it's caught in the dendrites, it's processed in the soma, and it is traversing through the axon. And at the end of this, other neuron will be there. So it's a set of neurons. It's a network only. It's a network of neurons only. And when we say it is interconnected, it's not directly connected. Whenever it is needed, it will be getting connection. That's it. It's not all the time, it's not connected. Whenever it is required, it's getting connected. And the connections are done through the synapses. So these are the main 3 terms here. And you can see, this is, if I take the cross-section of the synapse, this synapse will be having a neurotransmitter where I'm not going in detail for the biology and all the type of things, but just for the awareness, dendrites will be capturing the electrical signals. It will be processing there in the cell body, near to the presoma, and then it will be going through the axons, and then it will be reaching the next end. It will be reaching the next end where the synapse will be there, and whenever some activation is being done, the signals will be transmitted like the ions, the chemical or electrical impulses, maybe some ionic exchange. Whenever it is needed, it will be opening and it will be traversed to the other one through the dendrite. So synapse is the transfer, and it's getting triggered through the synapses, and now we can connect this. When we are going for our deep learning, we can connect the synapses to our activation functions. It is like our activation function. It's whenever the impulse is triggered, whenever some action needs to be taken, synapse will be transferring that to the next dendrite and it will be moving. So this is how it is getting coordinated, and we are able to identify the object, we are able to move our hands for catching the ball, or when we touch the fire, we are able to sense that it is hot, and we are able to withdraw the hands. All this coordination is being done like this transfer of the impulses. And now let's move on to the learning process. As we all know, the learning process starts with a baby. Baby, when it's born, it don't know anything. It cannot identify the images. We have little knowledge. We learn something, unlearn something, and then we will relearn again. That's what happening in our cases. And for the baby don't know anything. First time when the baby is seeing a cow, the mother or the father, or they will tell him how to teach him. Tell him that this cow's head is like this. It's having horns. It's having eyes, ears, the length of like something. They will tell, and they will show. There is a typical learning like telling the different babies is different. How we will tell the features to identify a cow, like cow's head, how we will identify, and then cow's body, like cow will be having 4 legs, then tail is there, the length of the body, all these things we will see. We will tell the baby, and some neurons get excited, and when the baby sees the cow for the second time, the baby is able to identify the cow. Maybe the learning take, like we will tell weak learners are there, good learners are there, and very fast learners are there. If it's a fast learner, next time when the baby sees the cow, it will be able to identify the cow. And if he's a slow learner, it will take little time for him to identify. The learning process takes little time. But whatever it is, some neurons will be getting excited. It's trained. It is getting the information. And then we are not telling the cow about the color or anything like. When it is a cow, we will be telling him about the features, like the head will be like this. If you are telling only about the colors, what will happen? If I am telling the baby that black and white, if it's a black and white thing, it is a cow only, animal with a black and white color, it's a cow. Then next time when the baby see a dog or a goat with a black and white color, he will identify it as a cow. So color alone won't work. Why I am telling this is features, the minute features are also very important in the learning process. So when we are giving an image, suppose we want to identify a tumor, if we are giving an MRI image, and then maybe it's a very small point, maybe in a very small point the image that the tumor is identified. So each minute feature is very much important in the learning process. So not one feature alone. That's why these neural networks are helping a lot. We have a lot of hidden layers there, and with the help of this lot of hidden layers, too many learning processes are happening. Features are extracted, it will be marked with the weights, and again back propagation is happening, weight balancing is happening based on the error ratio, back propagation is happening, again it is recalculating the weights, and finally it will reach at the correct one and it will give the output, proper output it will give. See, next time the baby is seeing a different cow. It's seeing a different cow. So first it had a learning experience that one cow looks like this. With is adding some more neurons are added to that, and the baby is able to identify that also. So the learning process, it is a gradual change. The learning process is gradually happening, and some more things are getting triggered. Then when it is seeing a car, some other neurons are getting triggered, and the baby is able to identify. I told them there are more than 86 billion neurons, and I have shown you the probes there. Which are all probes are helping for finding what all things, the frontal lobes, the sights, all these things, and sensations, all these things, different parts is coordinating, and finally the cerebellum will be coordinating all these things. So this learning process is happening there, and the baby is able to identify a cow as well as a car. Okay. Now let me little bit enhance this. This is the picture of a koala. Koala is a bear. If anyone is familiar with the deep learning algorithms or deep learning, this is a classical picture where we use. This is a classical figure. Koala is a bear in Australia, commonly found in Australia. And see, here I am adding one more layer. Here I am, see, feature extraction is happening in the first phase I told you. So how to identify the features? How to identify? So if I am splitting this as two layers, suppose if I am dividing this as two layers, first layer, the head portion is identified maybe, and in the second portion, suppose in this example, the lower portion is being identified. And in the first portion, when head is to be identified, what is being checked there? Is it an eye, nose, ears? The position of the eye, nose, ears, and all these things are learned in some portion, and it is identified. Then the assumption is made that it is a head. And if the hands are detected and the legs are detected, and that portion, if it is marked, we can assume that it's a body. And finally, if the head portion and the bottom portion, two portions are marked, we can tell it is a koala. Right. So this image, in the learning process, again there are different levels of learning. Different levels of learning, we call this as the feature extraction, different processes of learning. The minute features we will identify, and then we will find, coordinate all these things, and then there are different stages are there. Okay, before going to the detail of this, again, let me bring a comparison between classification, detection, and segmentation. So classification is identifying an object. So some 10 fruits are given, or a cat, dog, everything is given. Identifying which fruit, which one is orange, which one is apple, from the group, identifying that is known as identification. And then locating, object detection, this is finding place in our cameras, AI road cameras and all. Then in the airports and all, locating people, detecting the object and locating the objects. With the segmentation I'll come later, where we are drawing the pixel-wise separation is being done. And UNet is a famous segmentation algorithm which that I'll be explaining later. So which pixel belongs to which object, that will be explained in the segmentation. So the detailing, more detailing it will be there, and sometimes the segmented images are given as the input for learning, so that the learning will be more easily. The learning will become more easy. The segmented images are given as the input. Okay. Now let me move to the classical example algorithm, the CNN. CNN is how many of you know the process happening in the convolutional neural network? How many of you know? Yeah, I'm not going to ask any questions. If you know, please tell me. Okay. I just want to know how deep I should go. That's right. See, so if you know one algorithm well, you can develop the other algorithms. So convolutional neural network is an algorithm in neural networking, which is very effective for image classification. It's very effective in image classification. Image means any type of images. It can be medical images, it can be other images, the image classification. And I'm showing the deep CNN algorithm where we have the fully connected layer also. So in the first CNN models, we had layers only, the feature extraction layers and the output. And when it was found insufficient, again one more layer is being added there in the deep CNN, which is known as the fully connected layer. Again there some more convolution operations are happening. CNN stands for convolution neural network. And in convolution neural network, there are different processes which is known as the first process is the convolution operation. And the first step in the, maybe you must have seen the feature extraction and the classification. First when I had shown you the difference between machine learning and deep learning, feature extraction is a separate unit and then classification is a separate unit. So here feature extraction is being done in the first part and then classification is being done in the second part. And in the feature extraction, we have the convolution, then pooling. Convolution and pooling is there. You can see one more thing there, convolution plus ReLU. ReLU is the activation function, I'll come to that later. Then convolution and the ReLU layer. What is convolution? I'll go into that. See here, this is all these processes. The first process is being done for the feature extraction. So we are going to extract minute features from the image which is given, and then finally the cumulative of all these things, when it is flattened and it is going through the fully connected layer, it will give the proper classification output. So this is the, just you can see the pixels. Then edges are identified here. For this is the cell identification. See, the edges are identified and then some more edges are identified. Then some other parts are identified and then some other parts are identified, and finally you will be able to get the output here. So convolution operation, what is happening in the convolution? It is a filtering operation first. Okay, let me tell you. When an image is input, it is seen as a matrix. It's seen as a matrix, and if you want to extract some portion, okay, let me take, normally we will be taking bigger images like 1024 by 1024 and more. Don't go for the complication, just let me take a small image and what is happening there in the convolution layer. So here I am taking a 6 by 6 image. Okay, here I am taking a 6 by 6 part. 6 by 6 part only is taken and a filter is applied on this. A filter, first in the convolution network, first thing is the filter, applying a filter on the image or the image portion extracted. And this we can have in the neural network, number of neurons will be there and we can have a number of filters also. Okay, we can have a number of filters also. And if the image is black and white image, the numbers will be here in the matrix represented, it will be spanning from 0 to 255. And then if it's a colored image, then RGB will be there, 3 such 0 to 255 will be there. So by 3 also will be there. So if I am telling here as 6 by 6, this will be 6 by 6 by 1. And if it's a colored image, it will be going as 6 by 6 by 3. Okay, and I can apply a number of filters. First, let me take one filter and show you how the filtering is happening. So, filtering is a mechanism, or filter or kernel or feature detector we call it as. It is a mechanism for reducing also, extracting the feature as well as reducing the size of the image. So here you can see I had applied I had an input 6 by 6 matrix and a 3 by 3 filter is applied on it. A 3 by 3 filter is applied on it, and what output I am getting? I am getting a 4 by 4 matrix output. 4 by 4. How I will assume that I am going to get a 4 by 4 matrix? So it is based on this. If I have an n by n input, and the filter size is f by f, then the output from that it will be n minus f plus 1 by n minus f plus 1. That is my n is 6 here and f is 3 here, and my output will be 6 minus 3 plus 1. So 4 will be my output size, and again by 4 if I am doing. By 4 I am doing, so the same thing, n by n, f by f, 4 by 4. So I hope you got how you got from the 6 by 6, and one filter is applied, and this 4 by 4 output I am going to get. Okay, and then how the convolution operation is happening. See, I will be getting 4 by 4 output, right? But what will be the content of the 4 by 4 matrix? That's our interest next. What will be the content of this 4 by 4 matrix? So how you will fill this 4 by 4 matrix? There comes one more term which is known as stride. Okay, there comes one more term which is known as stride. S-T-R-I-D-E, stride. And so there comes one more term, stride. And based on the stride, we can extract the features, and the value also may change. I'll show you how. See, first I am applying a stride of 1. See, first step what is happening? First step. So I have the matrix. See, this one. First I have this matrix and this one. And then okay, so if I am applying a stride of 1, that is I am just moving one block. I will show you the animation later. I am moving one slide apart. So what happens is, this image I will be superimposing on the 6 by 6 image. Okay, so on the 6 by 6 I will be superimposing this one, and the first one, take the first 3 blocks. What are the content of the first 3 blocks? 169, 2519, 374. Okay, so in my filter, so here, take this first 3. This I am going to superimpose this one, this matrix on top of this one. Okay, and the first 3 blocks will be 169, 2519, 374. So the first one will be, this one will be multiplied by this one. Then this 6 will be multiplied by this 0. Then this 9 will be multiplied by this minus 1. And again this 2 with this 1, 5 with this 0, and 1 with this minus 1. And again 3 with this 1, 7 with this 0, and 4 with this minus 1. And you will be getting the first value for this. For filling this 4 by 4 matrix, you will be getting the first value there. That is the first value. Adding up all these things, whatever you are getting, that will be the first value there. And how to choose this filter, I will tell you later. These values are not pre-filled. This is learned, and then finally the values will be assigned. Initially we will be starting with some error and trial method, maybe all filled with zeros or some other values, and later after learning process, after repeated learning process, this weights are correctly. This is correctly balanced. Okay. So here you will be getting this one. If I am going with a stride of 1, okay, if I am going with a stride of 1, after this block, I will be moving from here. I will be moving from here. Again, I am superimposing this 3 by 3 on top of this one, and I will be getting the second value over there. And again, if it is stride 1, moving one bit ahead, and again I will get the 4th value. So let me show you how you are going to get the value. So in the first step, now I think you will be able. So first I am going to superimpose that filter on top of our image 6 by 6 image I had, and there I am calculating all the values. As I said, you will be multiplying each value and adding up the values, and as a result, see 1 into 1, 2 by 1, 3 by 1, 6 by 0, 5 by 0, 7 by 0, -1, 1 into -1, and ultimately I will be getting a value -8. That will be the first value over there. That's the first value for my feature matrix, what I have got. And how I will get the second value? Second value will be like this. I will be moving this to the stride 1. If I am using stride 2, 2 places I will be moving. Since I am using stride 1, I will be moving this to this position and I will be getting the second value by multiplying all these values. And again, we are not multiplying all these values when we are writing the program. It will do, but we should know how the convolution operation is happening. Okay, so that is the easiness. Like the algorithm will be doing all these things when we are implementing CML. If you give convolution 2D, con 2D, and in brackets if you give how many filters are there and what is the size of the filter, it will do the learning process and it will give you the values. But you should know how the values are obtained. At least you should know about CML. Okay. Then this process is repeated. This process is repeated and finally my feature map is filled and I am able to get the output. So this is how, see now you can see I have input as 6x6 image. I have given not 6 by, normally the images will be of high size, but for simplicity I have taken a 6x6 matrix and this 6x6 matrix is now reduced to 4x4. Okay, now it's reduced to 4x4. Now let me show how the convolution operation is being happening. Just to see how the convolution operation. How the convolution operation is being happening. See, this is my. What is this one? Can anyone tell what is this one? That is after equal to what we got. That is the feature map, right? So this is my input, right? This is my input and this is the matrix I am using. This is the matrix I am using. Here it is 9 by 9, 9 by 9 and I am using 5 by 5 filter. Just to calculate and tell me 9 by 9 and 5 by 5, what will be the feature map? What will be the size of feature map? It will be 6 by 6. That is what we are getting, 6 by 6. It is 9 minus 5 plus 1. 5 by 5. No, not this portion. I do this one. This only 4 by 4. It is 4 by 4 only. That is the middle portion it is showing. I counted from there. It's only. This is 9 by 9 and the 4 by 4 filter only I am applying. I am applying the 4 by 4 filter, so it's 9 minus 4 plus 1. So you are getting the output as a 6 by 6 matrix. So this portion. See, so here what is happening in the convolution operation? First, it is starting from here. This is stride 1, so it's moving each and everything and then it will reach the end. So starting from here, first, so each value is getting filled and finally it will be reaching here. And here, can you notice any problem that after the break I'll tell you about this one. Can you notice any problem over here? Whenever scanning is being done, whenever filtering is being done, here this corner pixels, see the corner pixels, the other pixels are scanned several times, right? Just to look at this picture, here, starting from here, second one, third one, ever you see, again, it's coming down. See, only the corner pixels will be scanned one. So if any important features are there in the corner pixels, that may get missed. So we cannot keep in images, we cannot predict where the important informations are there in the corner pixels or in the other pixels. So we cannot leave that. For that what we do, we will be doing padding. We will be doing padding so that we will be adding extra things in the corner pixels. Either we will be padding by 1 or by 2 so that the important features in the corner pixels should not get eliminated. So for that we will add, simply we will add, fill with some zeros or ones, some 2 rows, 2 blocks we will add here. That is known as padding. So So that's the adjustment we are going to do in order not to lose the important features.
Here, two sections.
Ah.
I think it's the more thing. And the other two are tiles.
Which one?
There is a room 5x5 room.
Ah.
If you remove that 5x5, that is 2x2.
Ah.
2x2 is tile.
No, that's not that. Maybe go back to the But here, this may be the important features. Here, I am not telling about the padding. I will come to padding later. See, why this? That's what I wanted to tell. Here, this pixels are scanned once, so that some features may be missed. Maybe they must have colored it like, so maybe the 2x2 padding. Break for tea.
Now we have a tea break. So this we're happy.
The plates are arranged outside. We get 15 minutes. We can have it in
ഇത് പിടിച്ച് അമർത്തിയ ഓഫാവോ?
അറിയാമോ സ്റ്റോപ്പ് ക്ലോസ് ചെയ്യുന്ന അറിയാമോ?
ഓഫാവുന്നില്ല, ആവുന്നില്ലല്ലോ. ആയില്ലേ? ഇല്ല, പിന്നെ ഒന്ന് നോക്കിക്കോ. കണ്ട അവൻ ചെയ്യും. ഇത് വീഡിയോ ആണല്ലേ? ചേട്ടാ നമ്മളെ ആ രണ്ട് പിടിച്ച് അമർത്തുമ്പോഴേ അതേ ഓഫ് ആവുന്നില്ലല്ലോ.
N by 3 filters, 0 to 255. One will be for the black and white images, monochromes, and for this colored ones, RGB we will be following. Then I said in the beginning itself, we can have different filters, more filters we can have. This we can have more filters, right? And when we apply more filters, this is a typical example for the optical character recognition, the numbers, digit identification. In order to identify this digit 9, maybe we require minimum 3 filters like this. One loopy pattern we need to identify. Then maybe this area and maybe this area. So for this, here in this case, we are applying the three filters. One is a loopy pattern filter, then a vertical line filter, and a diagonal filter. So when the image is becoming more and more complicated, we may be applying more filters. Okay, we may be applying more filters for the images. Now, for detecting the feature, suppose for detecting a single feature, let me take up our previous example of the koala. Our koala example, the features detection, the filters will be moved across the image as we had seen in the earlier case, like the filters will be moved across the image. And here suppose I want to find the eyes. I have an eye detector, one filter I have, and I have moved it across the image and found the position of the eyes here somewhere. See in this image, we are finding this eyes here, and it is detecting the eyes somewhere around that position, that eye detector filter. It's able to identify the position of the eyes. And in the next image you see, same filter is applied, and the position of the eyes are at different place. The position of the eyes is at different place, and this filtering operation, it is able to identify the position of the eyes here. Okay, so this is maybe location independent, and it may be able to give the correct features. So how to program it, that's what we are going to see. Then again, this has to be location invariant. And then again see in this image, we have 3 koalas and 5 eyes are visible. One is not, see this koalas, 1 eye is not visible from this scene. And 5 eyes are there, and see this, it is, the filtering operation is able to identify the 5 eyes in this position. So we need in the feature detection one more thing, the location invariance. Wherever the filter is, when the filter is applied, wherever the location of that particular part, it has to be identified. And then now see a hands detector, where it is applied, only one hand is visible in the scene, and we are able to identify the hands in the scene. This is how the filters, various filters are applied, and how the feature is identified. Edge, first edge detection, other detections, then gradually we are going, and when different filters are applied, we are able to identify the correct location and correct part of the image. See now, you can see here, I am applying one eye detector here, then a nose detector, and then one ears detector. So in the first case, are you remembering? See, when I had shown you the neural network, the head portion was identified and the body portion was identified, right? And here in the head, filter for a head. And in the head portion, I am going to find, is it an eye, is it a nose, is it an ears? And then if everything is yes, then it will be mapping to, we are assuming that it is a head. So similarly here, the eyes are detected at this position, nose is detected at this position, then the ears are detected again, and then the head, for the filter for the head is applied. It is different layers. Filter for the head is applied, and I am able to identify one head in the image. So gradually the learning process is happening here. See in this case, head and body. So earlier I had just shown you with the networking, neural network concept, where we have two parts, like 2 layers. Here one head and one body detection is done, and here through the filters, different filters applied, eye filters, nose, ears, hands, legs, and then it is identified as head. One head is identified and one body is identified, and ultimately we are going to get the output as the koala. Okay. Now let me go to, before moving to the other things, let me go to the activation functions. What exactly is the activation functions? So once a trigger is electrical impulse in our human brain also, when impulse is triggered, if it has to progress, that activation has to happen. So that's what activation functions are doing in the neural networks. So in the learning process, if activation is happening, then the process will be transferred. The learning process will be transferred and we will be able to go to the flatten. First, flattening layers will be moving there. And hidden layer performs all sorts of computation on the feature rendered through the input layer and transfers the results to the output layer. And what is the role of activation function? It decides whether a neuron should be activated not by calculating the weighted sum and further adding bias to it. So this terms, bias, variance, all these terms, if I go on telling, so it will take again one more session. So based on the error factors, just now you consider that there may be error in training as well as there may be error in testing. So if training error happens, we'll call it as a bias, and if testing error is happening, we'll call it as a variance. And these factors all contribute to the error possibility in the output. So we will be reducing that factors. Okay, so this activation function, just see that a neural network without activation function, it will be only useful for the binary classification, whether it is only yes or no. No need to predict any other thing. Just it won't do further learning. And we need non-linear functions for, that is linear regression is a typical example. And non-linear functions will be used for the multi-layer classifications or multiple classifications. And there are many many activation functions available, and in that we will be, for multi-class classifications, we will be going with the sigmoid functions, ReLU, then leaky ReLU, all this type of things are there. And sigmoid we will be going for the binary classification normally. And then damage function can be there for the multi-class classification. And then usually whenever we are doing programs, we will be seeing in the first CNN example also, this ReLU was there, which is a rectilinear unit, ReLU, and it is just for activating the neurons or promoting the learning process for the balance in the weights. And then we have the sigmoid functions. Then apart from this, there are different activation functions, leaky ReLU, exponential linear unit, ALU, SALU, different functions are there. But no need, just we should not bother about all these functions. If we go on learning about these functions, how the graph comes and all, it will again take 5 or 6 hours for completing this. Just understand that activation functions are there for just propagating, doing the transferring the impulses to the next neuron. It acts as the synapse in our brain neural network, biological neural network. Okay. Next, let me come to padding. Padding, I said previously itself, some features which are very important may be missed. In the first scanning cases, we had seen that some features may be eliminated, may be missed. So in order to avoid that happening, that missing of some information, we can have padding for the image, so that we are not keeping any important information in the corner portions. See, if this is the case, this is some important features. Suppose this is some important features. When we are applying the filters, maybe this information may get missed. So in order to avoid that, we can have some padding there, so that we are adding some irrelevant information there, so that our important information will remain as such. You had seen the filtering operation where inner portions will be filtered more and more. Even we can fill with some other, no need you should all the time fill with zeros. You can fill with some other irrelevant information also for the padding. And when padding is done, the size of this one will be along with the, as sir asked there, that's why I did see image size plus 2 into padding minus kernel size will be the output actual, if you are including the padding. In that case, I have not taken padding. It may be padding or may not be padding. Okay. So this is padding. Why we are doing padding is just not to miss any important information in the corner pixels. And next is pooling. So in the CNN, see, I'll just show you. In the CNN, here you have seen, in the first feature extraction part, we have convolution and review layer. Some activation is happening there. It's moving there. And next is the pooling layer. Next is the pooling layer. What this pooling layer is doing? Pooling layer is only a size reducer. Again, our images will be very big images. And after doing the convolution operation by applying filters, we are getting little reduced size image, but still it's a big image only. We had seen 6 by 6 is converted to 4 by 4, so it's still a big image only. So we need still reduction in the size for progressing. Again, we are going for pooling in this context. And now see here, pooling, how it is being done. In pooling, there is no filtering actually happening. Only there are different types of pooling like max pool, mean pool, average pool. There are different types of pooling. Don't bother about the type of pooling. Whatever it is just applying the convolution operation, just for reducing the size. And here no multiplication like the filtering process is done. When we were applying the filter, we were applying some filters and we were multiplying with the image values, right? The values in the boxes. We were multiplying with that. But here in pooling what happens is, we are not multiplying with the values, whatever is there in the pooling we are applying. Here what we are using, this kernel size 2 by 2 with a stride of 2 by 2 is applied for this image. Suppose this is my original image. And I am applying a pooling for this 2 by 2. And here you can notice the difference between stride 1 and stride 2. If it was stride 1, next filtering that will happen. First it will start from here. Next 2 by 2 will start from here if it is stride 1, right? If it is stride 1, next filtering will be happening from here. And the next will be happening from here. Since I am using a stride 2 blocks will be moved. Like that it's doing. See here, first from this block, if I am applying max pooling, maximum value from this block. Maximum value from this block. What is the maximum value from this block? What's the maximum value from this block? 7. So 7 is extracted. And then what is the maximum value from this block? 3 is extracted. And what's the maximum from this block? 9 is filled here. And maximum from this block? 3 is filled here. So this is how max pooling is working. So when I am applying max pooling with 2 by 2 filter and 2 by 2 stride, the image is, you can see the image further, it is 4 by 4 image further is reduced to a 2 by 2 image. Pooling is just pulling down, just reducing the size of the image. If it was stride 1, you can notice here, if it was stride 1, it will just move one block ahead, one block. If it is stride 2, it will be 2 blocks. If it is stride 3, 3 blocks, it will be moving. So stride 1 usually we are applying because all the cases in filtering operations, most of the blocks will be moved at least once. At least most of the blocks will be visited once if we are applying stride 1. And if you are applying stride 2, the skipping will happen. That's why in most of the filtering cases, we will be applying the stride 1. Okay, this is further reduction happens and this is average pooling. In this average pooling, based on the context, we may apply max pool, mean pool or average pool. In average pooling, average of these 4 values will be taken. Here, just understand that there is no filtering operation like the multiplication and all is not there. Just the whatever value is available there in the block, from that maximum value or minimum value will be taken for reducing the size of the image. That's only happening here. So now we had seen in the convolution neural network, the feature extraction process, we have the convolution operation with the filters, and then the activation functions will be activated for propagating forward, and then we will be having the pooling layers there. So here the feature extraction is over, and once you are going for the feature extraction, what is the next stage here? In the convolution neural network, so in the feature extraction steps, we have the convolution operations and the pooling operations, and then whatever value, whatever image we are going to get, next we are going for a step which is known as the flattening of that thing. That is, now our matrix is multi-dimensional matrix only, either 3 by 3, whatever it is, 2 values are there, and now we are going to make it as a vector only. Single vector only, whatever values are available, we are going to make it as a vector. And again, this is known as the flattening operation. And this flattening, after this, again it is going through some operations, which is some layers which is known as fully connected layers, where again this filtering, pooling, all these operations will be there, and finally the classification is being done. So first it is half ready for the classification. We are extracting some features. That features we are flattening and making it into a vector. And earlier CNNs just this feature extraction and we were getting the output. And the outputs may not be that much accurate. That's why still we are going for the fully connected layers again, and then we are going to get the output here. So this is what I want to tell in the fully connected layer. In the fully connected layer, actually what's happening there is, this is also known as the dense layers. So when you are going for the practical implementation, you will be calling this as dense functions, dense layers. And if you introduce fully connected layer, you provide a model with the ability to mix signals. Since every neuron has a connection to single network layer, and it properly classifies the output. Again, in neural networking model, we know for each neuron there will be corresponding connections. So suppose this one is a single neuron value, then this one, and if this is the classified out, like if this is the second layer, then this one will have connection with all these things. 4 connections will be there. 2 will have connections with all these layers, neurons. Then 3 will have connections with all these layers. That's what. So in each layer, each level, the neurons will be having connections, all the connections with the different neurons there in the next layer. And finally, we will be able to get the output. See here, we are inputting this one. The cola image, and then finally we are able to classify whether this is cola or not. This is a simple example, and the same applies to the image. If you are applying an image, medical image, if you are giving an image of some tumor or something, is there any tumor identified in this position, or different categories of tumors are there, that also will be identified in these cases. And here, dense layer, how the learning is being happening is, each feature, see, our magical equation all the time we will have is sigma n is equal, 1 to I is equal to 1 to n, this wi xi, isn't it? So we will start with this from the perceptron, all these things. So the x will be the features and w will be the base. So whenever we are having these things, and if y1, y2, y3, y4 are the output values, if it's a four class classification, then if this is the base, and this will be combined with each features, and we will be getting the feature matrix, and propagating through the activation functions, if different layers are there, and then based on the loss function, the weight balancing will be happening, and finally this weights will be balanced, and we will get the proper filter, that is the magical number filled in the filters. How we are getting the magical number filled in the filters, whether it is -1, 0, 1, 0, or whatever it is. Initially, it will be starting with some numbers, and proper balancing is done. When the system is learning all the things, it will come back and it will do the proper balancing, and it will be doing the correct ways. This is how the correct classification is being done. I'll just show you the example of this one. Here, just to see, This is three types of tumors. Three types of tumors: meningioma, glioma, and the pituitary. Three types of tumors. So the images of three types of tumors. So when we are training the network, we will be training with each class different. One normal also will be there, and each class thousands of image will be training with. And I want to find out this one belongs to which one. So in the output, from this output, when it is trained in this network, you can find in the output, this is giving maximum value for 1. That means it is belonging to the first level of cancer. So this is how you are going to get the output. So when you are giving the image input, it will go through the feature extractors, classifiers, and finally it will be giving to which class it belongs to. So in this set, you will be having thousands of images. In this set, you will be training thousands of images, and in this set, you will be training thousands of images. And in normal case also, you will be having as a standard thousands of images, and finally, it will be able to classify which tumor, which category this particular input. This is suppose this is an image obtained from the clinical report of some particular patient, and when this image is given in the trained network, it will be able to tell to which tumor or whether it is normal. It's able to tell which one it belongs to. So from this output you can see that this belongs to the first class of tumor. So this is how it's helping us in different diagnosis of different diseases. Now I'm not going in deep for this, because my first session I thought I would complete till this in my first session, so that I can go in detail with the medical images in the second session. But now I'm not going in detail through these things. Here these are different variations of the deep networks. AlexNet is there. This is the variation where we have. The variation here is we have different layers, like here we have 5 convolution and 3, totally 8 layers with 5 convolution and 3 fully connected layers, different variations in features. And this came in 2012. Then GoogleNet architecture, this is a GoogleNet architecture or it's an Inception v3. And in this Inception again, it is again a set of convolution operations. That's a set of convolution operations. Whenever you are doing some projects and all, with the available data set, you may be applying all these algorithms. Like either you will be working with CNN, or you will be working with AlexNet, VGG 16, 19, all these models, and you will be comparing and you will tell which one is best suited for this particular one. That's how you are doing. Next is different categories. This is a VGG net, little more complicated structure where we have more convolution and pooling layers are there. See here by 3. Too many convolution and pooling layers are there. Then fully connected layers 2 in the VGG 19. 3 also is there. Some cases 3 also is there. Then again this third one is a softmax one. And then this is the example of an AlexNet, VGG 16, VGG 19. Why we are adding this more complicated structures is for getting the good input, good output. But don't think that if you add too many layers, too many hidden layers, you will get a very good output. That also will complicate the system, so that the learning process will become very slow. And ultimately it won't learn anything, and there again the problems like the vanishing gradient, all this will come, exploding gradient, vanishing gradient, all these problems. The slow learning will happen if you are making the system more complicated by adding more and more layers. Don't think that if you give overwork to some person, he won't be able to perform anything. So if you are adding more and more layers, there may be still problems, and finally the learning may become small because of the gradient issues. Exploding gradient, vanishing gradient, all these problems will be happening. So you should be very careful in choosing the layers. Now some of the recent trends, this also I will go quickly, and then we will move to the medical imaging, okay, in image categories and all. Yes, so the deep learning models in medical imaging, one model is some ensemble learning models where we have, what is an ensemble? It's a combination of different things. Ensemble is like, we'll be performing the operation with the different things and then combining for getting a better output. Maybe that is the ensemble thing. And again, as I told, this GAN-based models. GAN is a popular architecture which is very useful for segmentation as well as for classification, and this is able to generate new things. It is a class of machine learning framework and it's a prominent framework for the generative. From the name itself, it's very clear, generative. It's able to produce new things. It's able to produce new things, and here you can find different GAN variants for this medical image classification, DC GAN, Nano GAN, all these variants. There are different variants for in different applications, maybe for finding something with the anatomical things or something specific to the some bone related issues or specific to tumor related issues. We can have different variants of GAN, and this GAN is very supportive in finding the segmented results. And the advantage of this GAN is very prominent technology, and the advantage of this GAN is it's not a simple neural network. It is working based on two ideologies. There is a generator and there is a discriminator. There are some two complexities are there in this GAN. Generator will be there and the discriminator will be there. So generator is just generating some fake example. So if some input image is given, just some fake things will be given, like the encoder-decoder architecture. Some fake outputs will be produced to fool the discriminator. And the discriminator is able to find the fake outputs produced from the generator, and from that it's able to move forward for finding the correct masking or correct classification. So generator generates fake samples and tries to fool the discriminator, and discriminator tries to distinguish the real values. And there is one more term known as the transformers, and in this transformers again convolution operations are happening. So if some fake samples are given, that also it's able to identify. That's what. See, this is working with two architectures. Again, some fake things it's able to identify, as well as it's able to identify correct things, and again it's able to generate new things. So this is how this architecture is becoming very popular, and we know we are all seeking the help of this generative architectures nowadays, and this is very predominant in medical image analysis as of now. And again, one more thing is vision transformers. Vision transformers also working based on the encoder-decoder architecture. So here, in addition to the feature extraction, one convolution layer, more layers, not more layers, more architectures are involved here. And this vision transformers, they are able to produce by 4 terms computational efficiency and accuracy compared with the CML. So these are now very predominant. Transformers, GAN and all are very predominant in the medical imaging, and it's false proof results these things are producing. Okay. Okay, now let me move on to the medical images and analysis using Python. So here we had seen that from different sources we are getting the data. We are getting medical images from different sources, and there are different formats for the medical files also. That's where we have interest. different file formats. Usually we are going with the JPEG file format, MPEG file format, all these file formats only. And here in the medical images, more informations need to be embedded in a single image. For that, we are going with some other format like DICOM and all. It's not easily readable with the Python. So how you can read all this, I will explain in the coming slides. So before going to this, let me just give you an introduction of how which are the different technologies which give input images. See, in medical images, there are different technologies through which we get the images, right? So, commonly known one is X-rays. We know we will be taking the X-rays and that can be given as the input image. Then there will be impact of voltage on the X-ray contrast and all. Then we used to go digital, and there is another method of imaging is CT imaging, where for getting the images of larger areas and for getting more accurate results. X-rays will go better with metals, this bone parts and all. It will give good results. It will give just displays. And if you want to go with the other things, then bigger areas, we can go with the CT imaging. And the most prominent one nowadays, whenever we go for, with some disease, whenever we go for, first we will take, the doctor will ask us to take one X-ray, then we ask, it's not clear, just you go for an MRI. Right? So this is where we are able to represent the fluid parts also. As all of us know, our body consists of 70% of water, and the bone parts will be coming very clear in the X-rays, where the X-rays are passed and we are able to get the things. Radiation will be there, and MRI, the technology is different. So it is working through the magnetic resonance imaging. So the body part will be given to the, will be entering the magnetic field, and then through the resonance imaging will be there, and that image will be coming on some computer screen or somewhere, from where you are going to process it and you are going to get the output, and that will be more clear. And this MRI systems, we have two types of mainly. I am not very much aware of this terms, but just for the understanding, we have T1 and T2 imaging in MRIs, where on T1 images fat is represented as white, and T2 images both water and fat is represented as white. And in T1 images water is dark and the fat is white. And you can see the two images shown there, and this is how people are going to identify. The doctors, when they see, they are going to identify from the image which part is this one, which part is this one, is there any particular thing to notice in this part and all. They will be able to identify, and similarly when we are training the systems, that will be able to identify. And again, one more thing is, in medical images, there is some directional terminologies in the medical images, where we have different planes. In the different planes, like in the axial plane, sagittal plane and the coronal plane, you can see this is the different planar views of this. So these images are in the three planes. This is in the axial plane, and this is in the sagittal plane, and this is in the coronal plane. So different views, in different angles, different views are obtained, and this also helps the doctors for identifying the disease, so that different sections will be visible from this. And motion artifacts, like when patient moves during the image acquisition. During the image acquisition, if the patient, by knowingly or unknowingly, if the patient moves, there may be some changes in the images. See here, this is one image obtained without motion and this is some image obtained with motion, and correction can be done in such cases, and after correction what image is obtained, it is looking like this. So these all minute things are very important in the case of diagnosing the disease, right? And again, let me give you some idea about some good resources. These are some of the good books which you can just go for finding. This is Looking Within, Anthony Clinton. One book is there which is very good for the medical terms and all. And this is the Gonzalez book. Those who are studying digital image processing will be very well aware with this book, Gonzalez. This is a famous book. In this you can find so many examples and you can get idea about the medical terms as well as the images. Then now, let me show the medical imaging file format. So this is very interesting for us, as we have seen only the JPEG, the Adobe Illustrator files, PNG file formats, PSD, GIF and all. Right, see, here the images will be of different formats like DICOM, NIFTY, NRD, MINC, different formats are there. And this is a DICOM medical imaging. It's DICOM abbreviation for Digital Imaging and Communication Medicine. And in this DICOM images, a lot of informations will be embedded. A lot of informations will be embedded in the DICOM images, and it will be typically coming with a .dcm file extension. .dcm file extension. And for reading DICOM file, you need to have a PyDICOM thing in your library. Just I'll show the demonstration. I'll show you the CNN demonstration and all later, but now let me show you this one. It is very slow. Just let me show how you can. I think most of you are familiar with the Colab environment. How many of you are familiar with the Colab? You are doing your Python programming in Colab? Maybe 3-4 people. Whatever it is, it's a very friendly environment. Just to go to Colab and you can open the Colab. Just to go to Google and type Colab. Colab will be there, open new notebook and you can start typing there, and whatever files you are saving, it will be automatically saved to your Google Drive. Whichever mail is connected, your Google Drive, it will be saved, later you can use it. Okay, So here, just before going to the DICOM file format, let me just show you how you can load an image. Okay, how you can load an image into the this collaborative environment. Okay, so for this I am using some CV2 libraries, CV2 Python CV2 libraries. I am using some CV libraries, computer vision, and then this is NumPy. NumPy is for arrays, and import NumPy as NP. I am using this NumPy, and this is for plotting. I am using Matplotlib for getting the plotting. I am using this Matplotlib, and then in order to see my image, I want to extract the image from. My image is stored in the Google Drive, or if it's in your drive, wherever it is. My image is there in the Google Drive. I just want to import that image from there. For that, I have to use from Google Colab import drive, drive.mount, content drive. When I give, see, for running this, you just need to click here. Okay, for running this, you just need to click here. Okay, so when I am going to import an image, where the image is, it will ask you for the access for the drive. Okay, I have saved my image in my drive, and it will ask you the access for the drive. It will be asking like permit this notebook to access your Google Drive files. Okay, so no need to carry all the things, or no need to waste your memory space and all. You can just load in the drive, and then from there you can ask them. See, when I am giving this connect to Colab, what it is doing is, to which mail ID, which drive I should connect, it will ask. This network is very slow. See here, I have chosen this account. You can do the demo in the afternoon, no problem, just let me show. Then it is connecting there. So you can see the message over there. You can see the message over there, mounted at content.drive. So it is linked to my Google Drive. And I am accessing one image from there. So for accessing the image, I need to give imread and the path of the image, where the image is there. So how I get this path? How I can get this path? So here you can see one folder. Here one folder structure is there. You can click on that. You will get all the things. From here also you can take. So you click on drive, and you click on my drive. There I have saved my image. So in this, I have saved my image. test1.jpg. I need to take test1.jpg from here. So I have already loaded there, but I'll show you how to take. So here in this lab1 folder, I have many things. And from this, I am trying to load this test1.jpg. So how I will copy the path, or how I will get the path of this one. So here you can find 3 dots, right? And in these 3 dots, if you right click, you will find this copy path. Okay, you find this copy path, and you can paste the path here. Okay, so this path is this one. So this here you will be pasting this path. So I uploaded the image. So from this folder you can take. So here you click. Then from there, where you have saved your image, that right click and find the path and copy the path, exact path you give there. And then you give upload. So this is the image which is loaded. So this is how you are going to load some image. Okay, this is how you are going to load the image in your system. Okay. Here you obtain the image. How to size it? This we will go later. Here I have used one array, and then these are different filters. Different filters applied on this, and then different filters I have applied on this. We will go to this in the afternoon. And then when I am plotting this one, you can see this first convolution operation, edge detection is being found. Can you see some images? This is first level of edge detection being found there. This we will see in the afternoon. Okay, now let me show the different file formats. First one is first DICOM files. We were talking about the DICOM files, right? So now I have loaded a JPEG image. Now I have loaded a JPEG image. So it was direct. Just I need to take that from the drive and show it as IMShow. IMShow command will work and it will display the image. And in Python, for reading the DICOM images, you need another library, and that is PyDCom. PyDCom is the library which is needed for reading the DICOM. Not like the earlier case JPEG, you don't require PyDCom. Directly, if you read, it will image show will show you the image. But here you have to install. You have to get the library. For that, pip install PyDCom. If it's Anaconda, you have to give Fonda install this PyDCom, and that directory will be installed. Okay. So first you give pip install PyDCom. This is for loading the PyDCom library, which is essential for DICOM images, for reading DICOM images. Otherwise, if you are directly going and extracting that one, it will give error only, it won't read. So you need to first install the PyDCom. Here we have. So this is a DICOM file which is often found in the medical images. I'll show you what will be the contents of this DICOM files. Okay, let me move down and show you. See here, this is for accessing the contents of the drive. As I had shown you in the previous case, for accessing the drive, when you are giving this command, it will ask for the permission, and you need to give permission for accessing the contents from the drive, and you can import the contents from the drive by copying the path. You can add the path. So here I am trying to take one DCM file. Okay, so in my folder, in this folder, it's taking too much of time. Is it connected or what? Is it connected to internet or what? It's taking a lot of time. It should not take in some 1 or 2 seconds it will load. I'll show this, no problem. I have already executed, I'll show the output, but for them to work through it requires internet, fast internet is required. The afternoon, if you want to work on the images, then fast internet is required. And if all the people start using, I don't know how you're connecting using Wi-Fi or the LAN. But it's connected to LAN. Okay, let me continue with this. I have already discussed. See, now you know how to load this, how to get the path. Okay, so in my directory, I already have this file. Okay, I'll show you here. In my directory, I already have this DCM file. I'll show you from here. This is lab 2. Yeah, this is the file. See, this is the file. This is the file which I have. I'm trying to load. This is a .dcm file. Okay, this is a .dcm file. And how you will take this is, you need to just copy. As I had shown you in the previous example, you have to go there to the drive and find this one and right click and copy the path and you paste here. Then that will get loaded here. Okay. And then see, I'm going to print the contents of this file. You just see, I'm just going to print the contents of this file. So if you have a normal JPEG file or anything, you may not have that much content. See how much contents are embedded in this file. Here you can get all the information. I'll just scroll down and show you what all this much information is there in this file. See, here this will give image type. Then these are all some medical terms. Then the study date, study time, then modality. Many factors are there. For us, whatever is important, I'll show you. Then see the patient name, patient ID, patient's birth date, patient sex, all this matters, like who is the doctor attending, then series instant ID, series number, patient orientation, patient history. So many things are there in this file. You can just scroll down and see, not even these things, many informations. See, still informations are there. So many informations are embedded, like the disease type, the patient's details, patient's doctor's referring details, then what type of contents are there in this image. All these details can be embedded in a single image in the DCM file format. And if you want to change the patient name, all these things, and just let me show the image, what image it is. This image only it is, and that image was in the DCM format. So this is how you're going to read a DCM file format. And next one is DICOM. It is .dcm extension, and you require PyDICOM. And then another one is nifty information, nifty images. Then this is another file format where it will be coming with the extensions. it will be coming with the extensions .img, .gz and all. And for this you need a library called the MedPy, and then another library is the Nibabel. These are all libraries for used for the medical, for reading medical images. So PyDcom library you need sometimes, then sometimes you need the MedPy libraries, then sometimes Nibabel. So how we will install is using the pip install libraries for getting this library to your Python environment. So the most common mistakes everyone used to do is whenever you try to read the image as the other images .jpeg or other image types, it won't give any output, and you will feel that it's a very big mistake you have done and you are not going to get output. So you need such libraries and see the extension of the file which is there, and this is the biggest challenge with this with Python coding for the medical images. Which image type it is you need to identify. Then one more thing is, see here. See, let me show you the other one. Next, let me show you the other image. So this is a MedPy image. This is a MedPy thing. I am going to install. I need to install MedPy for this. Pip install MedPy for this. Okay. I need to install MedPy for this, and then I am reading this contents. And then see, this is the image extension nii.gz. So if you are seeing this nii.gz extension files, it belongs to, you need to install the MedPy files. So here I will show you the flare.nii.gz, how it will look like. See, this is the file. See, this is the file which I want to load. So these are all images. See, this is a JPG image. This is a JPEG image. And see the other images which I have here. I have many images. See, one DCM image is there, again one DCM image is there, and this is belonging to another class, nii.gz. This is also nii.gz, nii.gz, nii.gz. All these are different format images, and from this one, you cannot even identify whether it's an image or not. See, this again I have one more nii.gz image, and now see the content of this image. This I have one image, and see, if I am showing this image, I should have run and shown, but I share the programs with you, you can run. This is not loading here, it's taking a lot of time. If I stay after clicking this, no, it won't load, it will take a lot of time, but already loaded images are there, I will show you. So here, this is the image. This was the image which was there in that nii.gz extension file. And then, see, this is a masking being done. See, what is masking, I'll tell you. So if you want to, when you are doing the pre-processing and all, if some part is masked and other parts we need to remove, then the exact portion where you want to extract, you will be creating a mask and moving the mask over that, the other parts you can remove. If you have this area, some noise part in this area, I'll show you in another example. If you have some noises over here, and if you want to extract only this portion, if you want to extract exactly this portion, then you can apply a mask on this portion, create a mask on this portion, fix the mask on that, and then you can remove the other portions. That's what we are doing in the masking. So here I have created a mask on this, and then mask. I will show you the next one. These are the information labeled in Nibabel file, the contents of the Nibabel file. These are all medical terms, some things are there. Okay, then I'll show you one more example. These are all the information in this DCM file. As I had shown you earlier, all the information is presented in the DCM file. See, this is the image, loaded image, where you have some hue applied on the image. Then the soft tissue image, how it is extracted, how the bone portion is extracted. As I said, when we are going for this X-rays, only the bone portion will be visible more. Only the bone portion can be extracted. And how this is an original image, from that how you are extracting the bone portion and how you are going to extract the soft portion. And then see, this is the original image. So some processing is being done. This is a pre-processing steps where you can see in this image some noise contents are there. Like I don't want this things and all. Only I want to extract this portion. Only I want to extract the details, whatever details are there in the image. Only that portion if I want to extract. I am applying a mask. I am creating a mask of this one and applying a mask on that and then removing the other portion, and on the final image you can see here in the beginning this much noises were there, and now in the final image when the mask is applied you are getting the noise free image. You are going to get the noise free image. And then if I want to get the more zoomed view of this one, for detailed study, if someone wants the enhanced view of this, you can go for this one. And then cropping the image exactly. See here, again some unwanted areas are there, like some portions are there. Here, more portions were there. Only in this part image was there. Here, images were not there. And I just removed this part, and still this part is there. Here, little bit is removed. And here you can see the image only is taken, and more visibility, more view of the image. And then again enhancing. See, this is an X-ray image, and this type of images were very useful in the COVID-19 pandemic time and all, and even for finding the pneumonia cases, other things and all. This X-ray images are very important. And see, this was the original image, and this is the enhanced image obtained, from where detailing is more possible for the enhancement of the images. See, this is another original image, and this is an enhanced image of this one. These are JPEG images. These are all JPEG images, but only enhancement is being done for these images. Then again, it's still running the other one. And I told you about the directionality. Different views are there, different planes like the sagittarial plane, different axial sagittarial, different view planes are there. How to do that in this this one is, first one is, this is a segmented image, and they show me the different variations. Just we had seen here. Here we had seen the different planes. Just shown you the different views. Yes, the different views, like the front view, side view, or the things like the axial, sagittarial, coronal planes. How to implement this is, these are the different views. How to rotate the images. See, in different rotations, there may be some different features you can extract, maybe from some angle. And these are the different possibilities. How to extract this. This rotation is being done. And these are all the pre-processing activities being done before extracting the detailing. Yes, when we are doing with images or any, if anyone has implemented any deep learning algorithm for getting results, like any the optical character recognition or anything like that, then first there will be some pre-processing steps where we will be seeing the removing the noises, all then the rotation in angle, different angle, if any variation is there, all these pre-processing activities will be done. And then we will be going for the applying the filters, doing the operations. So pre-processing is very much important to get the first, remove all the unwanted things. So this is another image. Say this is the background mask applied, and then the mask applied on the plane, and then find clean image of plane. So this is different types of mask applied on the image, and these are all denoising techniques. These are all denoising pre-processing for removing the unwanted contents and getting only the needed parts. Only the needed parts. Okay, so this is the extracted image. Yes, this is the extracted image. So when you're taking some MRI or some X-ray, you may be noticing like there will be a lot of unwanted information in the image. And when it is given as an input to our algorithms, or when we are giving it as an input, this unwanted information, it may cause the system to work more for the learning process. So in order to avoid that, some pre-processing steps will be done where we will be doing the denoising so that only the image, correct image portion can be given and we can get the better results. Rather, in order not to trouble the system, you can give the correct image instead of giving all the things to the system. You can denoise it first and then you can give the correct image. For this, we are applying the pre-processing techniques. Okay. This is another one. Yes. Okay, now let me show you the image annotations. How image annotations are important. And for this segmentations and all, unit algorithms are very much important. Unit will be working with segmentations. Then what do you mean by annotation? Annotation is nothing but it's a process of labeling the images. Annotations are labeling the images. And in the first slide, I had just shown you the segmentation and the marking of the images. And this annotations are very important in, as you can see in our surveillance, then in the airports, in the road traffic cameras and all the things. So it is image recognition algorithms. First step, you may be doing it as a segmentation process, so that for getting the accurate results, like I told, denoising techniques are very essential for getting the accurate results. Otherwise, the system will be learning too much and you may not be getting the accurate output. And for getting the accurate output, accuracy in the output, what you can do is first pre-processing all this segmentation techniques can be applied and the segmented images can be given as the input. Here you can see even labeling also can be done. I think it is visible. Here in this images you can see the labeling also is done. This is actually called, maybe it's a bigger image, so it's shown as extra. Then in this image, whatever is there, bicycle, dog, all these things, labeling also can be done for the application. Here you can see the rectangle mapping for all the images. This is 3D representation. This is a 3D representation. And here this is a segmentation. And one category of segmentation is semantic segmentation. In the first slides, previous slides, I had shown you the segmentation. Right, in that segmentation, it's a pixel-wise categorization. It's a pixel-wise categorization. Here, see, in the semantic segmentation, what's happening is, along with the cat, many things are there present in the background. And this sky is there, trees are there, grass is there, and the cat is there. So pixel-wise detailing of all these things in the segmentation. This is one type of segmentation which is known as semantic segmentation. See, in this image also you can find different categories of things there apart from this cows. And if you differentiate in the first step itself, if you segment the image, and like I had shown you in the previous MRI, some unwanted things were there. We removed that and given as the input, then it will give better results. Like if you can identify the unwanted parts, if I want to classify whether it's a cat or dog, then if I want to give this, the unwanted information, if I can remove, if it's not required, then segment it and remove it and give only the wanted portion, then it may give better classified results. Okay, there are different types of annotations. The first type of annotation is bounding box annotation, where you can see the bounding boxes. This is most common, and this YOLO algorithm is very good in doing this annotations. Bounding in computer vision, the most commonly used algorithm is YOLO, which is doing this annotations very properly, and it's able to draw the bounding box along the image. Then another one is polygonal segmentation. You can see it is represented as a polygon. The image segmentation, it is done as a polygon, and the image is segmented and moved as a separate entity. So this is polygonal segmentation. Here the image is not segmented, just a rectangle is drawn over the image. That is a bounding box, just a bounding box is drawn over the image, and this is also a way of showing it as a separate entity. Right? Here the apple is shown by a bounding box representation, but here the image is extracted using the polygon segmentation. And then this is another type of segmentation is semantic segmentation. Another type of segmentation where I had shown you in the previous case. The semantic segmentation example I had shown you in the previous case. Here, this image, when it is semantically segmented, whatever entities are there in the image, that is represented pixel-wise, right? It is represented as pixel-wise. This much pixels is representing this cat, and this much is representing the trees, this much is representing the sky. More detailing is available here. And one more is in the volumetric way, cuboids, 3D cuboids representation. This is also like a bounding box representation, but it's in the 3 dimension. It's also a bounding box representation. It's a 3-dimensional bounding box representation. And it will be giving the depth information also for the object. So these are the different segmentations, and deep convolutional neural networks, they are applying this segmentation types for the marks and all the things. See, this is the input image, and 4 classes are there. 4 classes are there for this input image. You can see the 4 colorizations done for this. This is one colorization, this one, and this one. See, this is a multi-class problem where 4 colorizations are being done. And in the matrix representation also, you can notice the values for different pixels. See, as shown here, it may not be 0, 1, 2 and all, but that mask is represented with the same value. The particular mask is represented with the same value throughout. Right? Then multi-class segmentation. Another algorithm which is very important in multi-class segmentation is unit architecture, which is working with the encoder-decoder architectures. So here, why it got the unit name is it is having the shape of a U. You can see the shape of a U here, and VNet also is there. See, this unit is very good in multi-class segmentation problems. Here, this is an operation, convolution operation. Again, convolution operation, convolution pooling. Again, it's having here. Then here some other operations are happening. Then again, this is the decoder and this is the encoder activity happening. Decoder, encoder, and then you will be able to get the correct classifications for the multi-class classification. So this is identification of some cells. See, from this image, correctly identifying this one. Using the unit algorithm, and this is using some other algorithm. Feature extraction using some other algorithms is done, and here you can see it is correctly identified using this unit algorithm. See, the architecture for this is, there is an encoder-decoder architecture, then either it's known as downsampling, upsampling, and this is very useful. See, this is encoder-decoder network, very useful for the multi-class classifications. See, all these convolution operations and the encoding, decoding happening here. Now, let me give some recent areas where you can concentrate for research. There are often some research problems. One thrust area where most researches are being happening is the neural system disorders. In medical imaging, many areas are thrust areas, but neural system disorders like facial palsy, it's also known as Bell palsy. Many of you, I think many of you must have heard of this, or have you seen anyone affected with facial palsy or something? It's a neural disorder where some portion of the face will be suddenly lifted up, or some damage will be happening to the neural system, so that one fine morning the patient may not be able to open his eyes, open his mouth, or close his mouth, or sometimes the eyes will be open, he or she won't be able to close the eyes. And all such things are happening. It's a neural disorder, and it's also known as Bell palsy. And mainly two categories are there. It is affecting some parts or it's affecting several parts, and a lot of research is being happening in this area. If any research scholars or anyone is there, you can just read on these contents, and you can develop in this area. In the research, a lot of research is going on in this area. Then another thing is schizophrenia. Schizophrenia is another place where it's a learning disorder, and some memory issues, then some other related things, anxieties, then hallucinations, all these things will be. No, this is not a learning disorder, this is a small mental absent disorder where some hallucinations and all will be there for the person, and this person may not be able to properly concentrate on some things as well, and there will be some associated memory issues all with this patient. These are all neural disorders. And then one more area where you can concentrate is dyslexia. This is where you can have the difficulty with reading all these things. Difficulty with reading, difficulty in understanding something, some difficulty in learning some orders, numbers, all these things. Difficulty in some areas that's known as dyslexia. Again, this is a female-oriented one, preeclampsia. This is the mortality rate with the preeclampsia affected ladies are increasing now. So this is a situation happening in the pregnancy stage when sudden shoot of blood pressure happens because of various reasons. And there are various reasons behind this. A lot of studies being conducted in this area, and this is open research issue. Problems are there in this area. If anyone is interested in doing the breast care, see, earlier people were doing research in the breast cancer prediction, heart disease prediction, all these things, early detection of all these things, tumors, all. But these are all newly evolving areas where this is high blood pressure, and how it is, if it's not appropriately treated, the mortality rate may rise, and it is due to different factors, and how to identify the features, how to do the processing, all these things. This is an open problem. And again, this is another one which is known as glomerulonephritis. This is a special type of kidney disorder, glomerulones. Glomerulones are a special type of kidney disorders where so this is a normal kidney and this is a glomerully affected kidney. You can find the difference. See, the images will be there, scanning, CT scan, other things. And this is also an open problem. Many researches are going on in this area. So if anyone wants to explore, these are some of the items. If you read, you will get more items. I just listed few items, that's all. Thank you for your patient listening. Afternoon we can have the lab sessions. I'll share the codes with the coordinators. They will be sharing with you. Hope you will get a fast network so that you can do the programs. See, if you are doing in Colab, fast internet connectivity is required. Can you play? It's one side. Yes. Thank you.
Lunch break from 1 o'clock to 2 o'clock. So session, and the lab codes have been shared to your mail, so please access it.
All the lab programs are shared with you. Hope everyone knows how to run the Colab and all. Otherwise also you just go to the programs, whatever is given there. Just right click on the program. Open with Colab. It will directly open. See, 3 IPyNB files are there. This PYNB files are there, IPYNB files are there, 3 files, 2 image files are there, and data set, nothing to do with the data set. As is containing the images of all these things. We are not going to load that, nothing to do with that as of now. Just go to the lab 1 ITLB file, right click it and you can open it. Why it's not connecting? So in the first program, just I'll go through the program, then you start doing. Here I'm trying to read a 224 by 224 image, color image, and it belongs to number of classes. There is 10 classes, right? If it's fruits, 10 fruits maybe. And the morning I had told you about the CNN layers, the convolution layers, the pooling layers, the dense flatten, after the flattening, the dense layers and all. So first just a demo of the dense layers. Here, this dense layers, what it is showing is where the dense layers will come. In the classification phase, the dense layers will come. Below I have written all the convolution layers, dense layers, all the things together. First, this is the dense layers where we have given from TensorFlow. I am using the TensorFlow model and sequential. Why it is given sequential is in most of the programs, in the CNN applications and all, you will be noticing it as sequential. Why it's given as sequential? The operations, convolution operations happening there in the layers, that is in the sequential order, that's why we are giving it as sequential here. And then this is from, I told you, Keras API normally we will be using in TensorFlow. That's why I'm giving it as Tensor, nothing much, just I'll explain and they will be doing it, okay? They'll be doing it. So, TensorFlow.keras.layers, and since this is the dense layers, like what we have the fully connected layers. Fully connected layers, we call it as the dense layers. And here we are importing the dense functionality. And here I have 3 dense layers. One with the 32 neurons, then 64 and 128, and I am using the ReLU function for this activation. I am using the ReLU for activation of this. And I had the 10 classes, the number of classes was given as 10. And finally, we'll be using the softmax function for the classification output. And when you print the model summary, it will be printing the layers 32, 64, 128. That will be the number of neurons. This is the last layer, dense layer, not the convolution layer. Now, coming to the convolution layers, you can find, I will just show you the convolution and dense layers, everything together. In the convolution layers, you can find what all things are there in the convolution layers. Convolution operation will be there. Then max pooling will be there. And the flattening operation will be there. Then the final dense layers will be there. Okay. And the dropout is which all features. It's like a dimensionality reduction, or which all features are not essential, that will be dropping out in between. That dropout will be taking there. See, first come to the first one. Here you see from TensorFlow Keras we need the dropout, dense layers, flattening where we are doing the flattening. After the feature extraction we will be flattening, right? We have the metrics and we will be making it into as a vector. Okay, so we are doing the flattening operation there, and then convolution 2D usually we are using for the convolution operations. Then max pooling is being done. For the pooling, max pooling is being done here. And this is a sequential model. I told you why we are giving it as sequential. The operations happening in the layers is in the sequential fashion. So first my convolution operation here. See, I have 32. What does this 32 mean? What does this 32 mean? I have 32 filters here. 32 3x3 filters. Okay. So in the first convolution layer, convolution 2D, I am using convolution 2D is the function for the convolution layer, and 32 3x3 filters I am using. 32 3x3 filters I am using here, and the activation function, I said like our biological neuron, synapses will be there for the transferring of the signal, activation of the signal. So here we need to use the activation function. The ReLU is the activation function used here, right? And then next I have again 64 3x3 filters, and then I am applying a max pooling of 2x2 size, max pooling 2D of 2x2 size, and then dropout. Don't worry about the dropout, it is for essential features we will be taking, and the other features we need to drop out. And then flattening operation is being done. So just to remember what we had seen in the CNN, layers, first feature extraction. In that feature extraction, we will have the convolution operations, and then the pooling operation, and then we will be having the flattening layers, and then after the flattening layers, there will be the classification that dense layers will be coming into existence. So we are adding the dense layers. First here dense 128 means 128 neurons will be there, and then we are using the activation function ReLU over there. And the last for the classification, number of classes I had taken 10 in the beginning, and using the softmax function we are doing the activation here. And you will be getting the output. See, you can say I can take away 224 by 224 image, and after the first convolution operation it has become 222 by 222 with the 32 filters, and 220 by 220 64 filters. Then max pooling is applied, the image size is reduced to 110 by 110, and then this is flattened. You can see in the flattened layer we are not seeing any by 2 dimension. Earlier we had seen 224 by 224, 110 by 110, but now it is flattened, it is made as a vector, one single value only. So this many values will be there in the flattened layer, that is 110 into 110. That much values will be there, and then we are applying the dense layers, and finally the classification is being done. And this is a simple example of max pooling. This is a simple example of max pooling where you can run all the programs and just execute all the programs and can see the outputs. Here, this is for max pooling. And in the max pooling, this is 2D. You can see the array is 2273 12 4 72 7524 4125. This is a 4x4 matrix, and I am applying a 4x4 matrix, and in this 4x4 matrix, I am applying a max pooling of size 2, which is stride 2. So we had seen in the morning. In the 4x4 matrix, 2x2 I am applying, and with a stride of 2, what will be the output? What will be the output? If I have a 4x4 matrix and the 2x2 matrix with the stride 2, if I am applying, the output will be a 2x2 matrix. So this is the output for this 2x2 matrix. You can run all these programs and see all these things, because this will take when you are doing the epochs and all, it will take little time. Even this is very small, very slow net here, and I'll just show you this. You can execute. Even if it's not working, you can go home and execute. Okay, wherever you have fast network. I'll just explain the program. Then second one is second program we had seen in the morning. This you just to start practicing, otherwise you may not be able to load an image. Later you may find confusion from where to load and all. Those who are familiar with the Colab, there is no issue. Those who are not familiar with Colab, later you will be finding issue in loading the image. So here, after giving this command, after giving the mount command, when you click on this, it will ask for permissions. Okay, from which drive you are loading this program. First, you need to save the program. See, if you are executing this one, you need to save the programs in the drive. Otherwise, if you are executing from your drive, you need to make the changes in the code for reading from your local drive. Okay. So, you need to read from your drive, and then how you will take the images location, how you will copy the images path. You need to just click on this folder. See, it's not connected to network. You just click on this folder, and then from there, take it any time. So click on the folder where the program is loaded. There, right click and copy the path. Okay. So here, first you mount the drive. This you do now, as otherwise you will get confusion how to load the images. So this, how to get this path? Once you give access for the drive, just go to the folder. You will find this one folder here, and from there you right click and get the path. Okay. From there you can get the path and you can copy this path. Then you load the image, and here I explain this once again. Here I am applying 2-3 filters for this edge detection here. Okay. So here I have one filter. Filter is also having the name kernel, right? Filter is also having the name kernel. That's why I have given K1, K2 and all. And I am applying some 1 or 2 filters, K1, K2, K3, K4. And I am doing the filtering operations with 1. Then you see, when I am applying the filtering operations and showing the image, first image is this one with the identity which filter I have used. For identity I have used kernel 4 for this kernel 4, this kernel. I will show you how I got these values. Kernel 4 I have used for this one, and I am getting this output. Nothing is there. This is for edge detection I have shown, but nothing is being displayed there as it is learning only. That's not the correct filter to be applied for the edge detection. And when I apply the filter, identity 1 belongs to K5. Identity 1 belongs to K5. And when I apply this filter, you can see, can you notice anything here? Some edges are there. See, some edges are detected. In this image, some edges are detected. It was the old image. The image red was this one. This was the input image. And after the one convolution operation, when I am applying some filters, I am getting some output like this there. I am getting some edges detected. In your system, it will be more visible. In the display, it is less bright this way. And again, I am applying one more filter on this image. that is feature extraction, edge detection. And here again I am getting one more output, some edges are detected in this. So how I got that filters I'll show you. Here, if you take this third program, you can see there here, this is, don't worry about the data set used and all the things. Here, I'm using some model and some data set is loaded here, and I have divided that into training and testing sets. Don't bother about all these things now. Just when I am applying the model here also, I am giving 3 filters with the kernel size 3 by 3. 3 filters of size 3 by 3. Okay, 3 filters of size 3 by 3, and the activation function is radio. And flattened layer is used, dense layers are used. And when coming down, you can see the 28 by 28 image reduced to 26 by 26, and then the flattening 26 into 26 values will be there. Again in the dense layers I am using some neurons. And here, if I am trying to get the weight, I told you in the beginning itself, if you have an image input and then some filter operations is happening, what will be the values of the filters? We don't know about the weights, right? We don't know about the weights. The weight balancing is done after the learning and back propagation. And here, if I give the weights, you can see how many filters I have used? 3 by 3 filters, right? 3 by 3 filters. See, here 3 by 3 filters are used. Here you can see the values. This 1, 2, and the third value here, okay. 3 by 3 filters value, I'll just show you the values. Yes. So here you can notice, first 3 by 3 filter got value, second 3 by 3 filter, and the third 3 by 3 filter values. These are all initially some weights will be assigned, and later the system will be learning. It will be learning, and after the final learning again the weights will be balanced. That's what I am going to show you, because in the first figure, in the program 1 I had shown you some edges were detected after applying some filters, right? And here after that what's happening? After that one dropout layer is there, then see the operations happening there, and this is also random values applied here, and here, see here flattening is happening, flattening 2028 values. That 2028 values you can see here, these values are there, and then we are again applying the operations, and we are going to see after the values. See, last you will be getting the 10 classes. You will be getting the classification. Then, see, when I am going to train, this will take a lot of time. First I am fitting the model, and I am applying 10 epochs on the training set. Applying 10 epochs. Then, see, you can see after each epoch, the accuracy is getting increased and the loss function is getting reduced. It will be getting reduced. And after training, first beginning it was the random weights assigned, and after training if I try to get the weight, you can see the different weight values. I showed you the 3 by 3 filters were there. So earlier what were the values of the first 3 by 3 filter before training? What was the value of the first filter starting with the values? See, 0.1938 minus 0.37, not this one. This is, since I had so, see, this was the value, 0.275. This is the first 3 by 3 filter. Okay, this is the first 3 by 3 filter. And after training, let me show you the value. So I have trained it for 10 epochs, and after training, now I am getting the weights. You see the value of the first 3 by 3 filter. So the values are changed. This is how weights are being changed. So initially, the weights will be assigned some random value. Then training will be done. It will be moving forward. The process will be continued based on the loads function and all. The balancing will be done. Back propagation is done. Then gradient, all the things will be considered, and then again it will be balancing the weights. Now you can see after the first training, the values are different. So finally it will get balanced and it will give the correct output. See the second 3 by 3 filter. This is the second 3 by 3 filter, and again the third 3 by 3 filter. See the third 3 by 3 filter value. Then other operations. Then flattening, everything is being done here. And the different classes of classification. And you can again, I am training it for 5 more epochs. Suppose I am training it for 5 more epochs, and now you see the values, variation in the values. After training it for this training epochs, it will take time. Okay, if you are training, each epoch will take little time, and it will take more time. Here I don't know how it will work. See again after training, you just check. I am training this for again 5 more epochs, and again I am getting the weights. See the weight changes. Now when I am taking the weight, the kernel values, the filter values are again changed. So initially we were doubting how to take the values, whether to give it 1 0 minus 1 minus 1 0 1 and 1. We are not giving the values. After training for some time, the system will be balancing the weights, and finally the weights will be balanced, and the magical number in the filter will be filled. That's why. And then we will be getting the correct. See, the system will be balancing. So this is the next one. After again training for 5 more epochs, you are going to get this first filter value, second filter value, and third filter value. Now I will tell you, from here somewhere I had taken this, and see here when I had applied this filter, you can see when I had applied, here I have different filters, right? And to my image, I had applied one filter and I got this output. Maybe the first filter, maybe some values from the first filter where proper training was not done, and it was not giving, it was not able to detect any edges. Okay, feature extraction first stage is not able to detect any edges, or it's not giving any output, only blank it was giving. I had given this as the input, and first filter is applied. I am getting this as the output. I am not getting any output here, right? See, now you can see after the training I got one more filter, right? I had shown you the different filters, different values of the filters. After training you got different values, right? If I am taking one value from the trained one, and again when I apply it in the image, maybe in the image, see, you can see that it is able to identify some edges. It's able to identify some edges. So this process is continuous, and we will be training with more images and more types and more kernels, more filters will be applied, and finally it will be learning something and it will produce the output. Here, this is identity 1. Identity 1 is like identity 1, this value. This value. So this is one filter which was able to give some edge identification, some edges it had identified. So when you run in your system, it will be this figures will be more, images will be more visible. You will be able to identify some edges. You see, you can see here some light colors, some edges are identified from the image. And this is another filter applied on this, and we also in this display not visible, but here some things are visible. So after training, it's becoming more and more visible. So this is the first set of programs which I have shared. This is just for convincing you that this is working and you are able to identify the features. Identify the features after each weight balancing and after training the ECOGs and doing the process continuously. Okay. And then this all. This is the first set of programs, and second set of programs, you will have all the different formats of images and annotation values, all the formats, different formats of images. See, this is the DCM format file, how you can load the DCM format file and how you can get the output and what all things will be there in that. Then how to do the MedPy or that type of images, and then pre-processing activities. I think this all I had shown in the morning, and then this annotations is there. Directionality, different things. Then annotations I will show with some other image. See here I am importing one image and you can see this polygon is extracted. Polygon extraction is done, and see one image here. One image here. People are, 3 ladies are sitting on sofa, and from this, in this image, see this file formats will be different. JSON file. Importing here, that files, all the things are shared there in the library. See, I am importing a JSON file here, and in my folder that file is there, whatever is shared, it is there. Then that values, shapes I am extracting, and see the annotations done on this. That is the segmentation done on the values. Segmentation done on this. You can label it also, no problem. And this is the segmentation done on the image. Whatever image is given, segmentation done on the image. And see the rectangle drawn for this, the image. Even we can remove the colorization also, just a rectangle marking also you can run. This is how you can do the annotations on the images. And this is an annotation which is done on a medical image, where whichever area, if a particular area is finding some tumor or some particular difference in some particular area, if you want to mark the area, you can mark the area. These are all extraction methods which are very important. See the segmentation done here, 3 parts. I needed to extract 3 parts, and 3 parts are extracted from the image. That is, segmentation of the 3 parts is done. So if it is easily identifiable, this, if it is given as the input to some other deep learning algorithm, it will be able to easily classify to which group it is belonging to and what exactly will be the disease. All the predictions can be easily done by doing the annotations first. Then masking I had shown you in the previous class. In the morning class I had shown you the masking, how to remove the unwanted things and how to enhance the images I had shown you in the morning. So now you just try for the second program, loading the image and doing that. Second program algorithms and all you can implement later, or lab 2 programs you can start. workshop